Christ. Alright, so Conics. Conics. So it's one of my personal favourite topics in the whole course, okay? It's really an extension to the locus and the parabola, okay, and also an extension to the parametric works done in extension 1. Alright, but it's different to what you've experienced before. So, what are conics? So, a conic or a conic section is defined as the locus of a point which moves so it's distant from a fixed point, the focus, and the fixed line of the directrix is in a constant ratio. Okay? So, this ratio is called the eccentricity, and that's the notation of E. We're going to see that a lot this topic. Okay? So, we'll talk about that in a moment. So, conic sections result from a double cone. Okay, so joined at the tip, so we've got double cone, okay, which is formed by a generator. So essentially you've got a straight line at some angle and rotate around that straight line, which forms that double helix cone there. Okay, so the conic section is a cross section of that double cone formed by slicing a plane along the solid. Okay, so we've got that plane, we're slicing it that way, and we've got this conic here, which looks like a parabola. Alright, we slice it sort of parallel to the base. We have that conic. What do you reckon that is? Circle. Okay. We slice it along this way. Okay, so that it slices on the same slant height. Here, what do you think that conic's going to be? Okay. Oval, which is called formally an ellipse. Okay. So that's what we're going to refer to in this topic. Now, if we slice it in this direction, okay, we've got that and that. What do you think that's going to form? Yeah, it's going to form a hyperbola. Okay, and we'll talk about those as we get through the topic. Right, so considering slicing a cone or the indefinite length of semi-vertical angle alpha, okay, with a plane, consider slicing cone of indefinite length of semi-vertical angle A, okay, so the vertical and the slant make the angle of alpha, with the plane make an angle of theta with the vertical, okay. So depending on that value for theta, so when we slice it with the angle theta with respect to the vertical, we'll have those different conics that we just mentioned before, okay. So, also assume the plane does not go through the vertex, okay? So when we go through the vertex, like sort of straight through the vertex and nothing else, we're just going to get a point up. Alright, so we're actually looking for the conic. So if alpha is less than theta, which is less than 90, okay, so the value of this, which is less than that, and this value is also less than 90, okay, we have the closed cross section formed here, and that's our ellipse, okay? Now, if theta equals 90, okay, so we drop it sort of parallel with the base, so theta, so that sort of angle there is 90, okay, so we've established what happens when we cut it parallel with the base. We're going to have a special ellipse, which is what we formally call a circle. Now, if theta equals alpha, okay, so that angle with the slant is equal to that, and the same as that, okay, we are going to get our parabola. Now, if if 0 is less than or equal to theta, which is less than alpha, okay, so we're going to have a cross section of a hyperbola. Okay, so there's the portion of it there, okay, so of course this will be double cone, so it'll continue up this way, and we also have the rest of the hyperbola up here, so we're thinking about asymptotes and that sort of thing that will be formed with that in there. Now, of course, we already know what the conic forms when the locus of a point moves, that a distance from the focus and the directrix is equal, and that's our definition for the parabola. Okay? So, by definition, the eccentricity is equal to 1, so E equals 1 for our parabola. So, a circle is a unique type of ellipse, so technically we have the directrix of a circle which is undefined, so we assume that the eccentricity is 0 for the ellipse.